Welcome to the Picture Language Seminar. It's a great pleasure today to have Assaf Naor from Princeton. He's an expert on metric spaces and has won many awards and will tell us today about vertical versus horizontal isoperimetry. Assaf.
Thank you. Let me share my screen. 1 second. Share. So everybody sees it. Let me move this picture. Okay. So the way I'm going to do this is I'm going to write on the screen, but I'm going to show you pictures when we arrive there. I have a file with pictures. Thank you very much for the invitation. When I was asked to talk about the Picture Language Seminar, I went to your webpage and I read what this is all about. And I was thinking about the topic. I chose a topic which is about, most of the results about a paper which is 2 years old. It was posted in, I think, in May 2020, the height of the pandemic. So it's not the newest thing I did, but it has a lot of pictures. So, and most of the things that I work on are very high dimensional and they're hard to, it's more of a mental picture. But this is going to be, most of the pictures are going to be in 3 dimensions. I should say that the pictures I'm going to show are from this data paper are due to my co-author Robert Young from the Courant Institute, who, in addition to being a great mathematician, is just a gifted design artist, and he can make computers do the things that I can't even dream of doing. So the nice pictures are his design. Okay, and I don't know if this really fits into what you imagined for picture language. The pictures did play a role in proving theorems. They played a role in the sense that these were examples that we were trying to construct as counterexamples to the theorem that I'm going to show. And the examples taught us what we should be proving, what we should be trying to prove. But the proof itself has things which is not shown in the pictures, and in the pictures, and you will get to it. The one final thing, so the most recent result is available online. It's been posted in May 2020. It is, I had one funny experience with this paper. It's just an anecdote related to the pandemic. It was really the height of the pandemic, and after I posted it, I started getting bombarded by emails related to things like biochemistry, etc. And what I realized is that, so the paper has 3 words appearing in it, which some bots, like at the height of the pandemic, you don't want to post a paper like that. So the word corona appears actually in the title. That's reference with the corona theorem of Carlson, which we will get to. The word variant appears in several places. Whenever there was a step, it was a variant of a known step. And the 3rd word that appears in this paper, if you search it, is contagious. And this, I will, if somebody asks in the end how the word contagious appeared in the paper. But when you post the paper in May 2020, with these 3 words in it, you should see what happens to your inbox. I mean, nobody can go back in time. But okay. But all of these things have nothing to do with what was going on. Okay, so now let me start. I am not going to assume any background on the geometric analysis which goes behind, which is really the proof here. I'm going to define everything, but please, if I forget to define something, please stop me. I really, really am happy to answer questions. I know this is a mix of people in different areas. If you ask a question and you type it, then there's a good chance that I simply won't notice until the end of the talk, because I'm not good at noticing written questions, but I really, really like to be interrupted. So just speak up if you have a question. Okay, so I'm going to start with a very, 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 I really no need to define anything. I'm going to be describing an isoperimetric problem in the discrete Heisenberg group. Which I will define. And I will explain I'll show what it's good for. It's good for several things, but I will show something that it's good for. But then I will pass to the proof, and the proof happens in the continuous world. So I know many people here are actually used to the continuous Heisenberg group, and this is really how I think as well. I agree with all of you, but I just need no background in order to present the question in a discrete setting. And also actually the applications, there's applications to computer science happen in the discrete setting, but the whole proof and the whole intuition and the pictures that we'll see later happen in the continuous world. So be patient if you don't like the discrete Heisenberg group. But let me just start with the definition. So, you don't really need anything. I can just define it. And for the first 30 minutes of the talk, you can only think about generators and relations. So there is for every k, there is a group which I will call H2k plus 1. This is the k Heisenberg group. And it's generated. I'll tell you what it is in terms of generators and relations. So generated by, let's say, A1, B1, A2, B2, etc., up to AK, BK, and then an element C. And the relations are that, so the commutator, so A1 inverse, B1 inverse, A1, B1. So the commutator of A1 and B1 is C, and also A2, B2. AK, BK, and everything else that you see here commutes. And everything else commutes. So you want the relation, so what it's AI, BJ, and AI, AJ, and BI, BJ. What else remains? And C, AI, and C, BJ are all the identity elements. Okay, so this is the presentation. This is a collection of words that and this is the definition of the Heisenberg. So the fact that C commutes with everything else means that it's an element of the center. It's a central element. So this is just these last two constraints. And AI commutator with BI is the central element, and everything else commutes with each other. Okay, so this is the definition concretely, and you can let's keep it in mind. So the theorem that I'm going to be showing, and this is a surprising fact, it's something that I did not expect would happen, and I will explain something very intriguing. But the theorem that I'm going to show you has a different behavior when k equals 1 in the first Heisenberg group, and when k equals 2 and up. So there is a different qualitatively different phenomenon happening between them for H3 and H5, and so I will always actually in this talk discuss H3 and H5, but this is just for the simplicity of the talk. What's really happening is H3 versus all the others, 5, 7, etc. So when I ever mention 5, I really mean 5, 7, 9. They all have the same behavior with respect to this theorem. So H3, if you want a concrete representation of it, it's just all the upper triangular matrices, and then put an integer here. So the generators are going to be 1, 1, 1, 0 below. Let's say A1, and then B1 is the remainder is 1, and then C, which indeed commutes with everything, is the last matrix. Okay, and so there's a little exercise to prove that this is the same group. Right? The fact that the matrices satisfy these commutator relations is easy enough to show that this is that completely characterizes the matrices. It's a nice exercise. And then 5 is the same thing. It's upper triangular matrices, 4 by 4 matrices with 1 on the diagonal, so 0 below, and you do Z, 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 and then 0 in this entry. So the central element is going to be when you have 1, this top right corner, and 0 elsewhere. And the A's are going to correspond to the top row, and the B's are correspond to the last column. Okay, and you can check that this is a group. So this is really concrete matrix groups. And again, you have to prove that H5 is the same group as the presentation that I wrote. Okay. So, but this is so. But the reason I want to mention this matrix formulation is that I'm going to be drawing pictures, and so I really am going to identify H3 with it's written here. There is a it's just the 3 by the integer grid in the room you're sitting. Okay, so it's a 3-dimensional integer grid, and identification is going to be 1, 1, 1, x, y, z is going to be identified with the vector x, y, z. So this the direction in the top right corner is the central direction. I always call it the vertical direction, and it's going to be literally in this identification, the vertical direction. You're going in the z direction when you move in the direction of the center. And like the same thing in H5, I'm going to identify with a Z5 of this, because this is still discrete. And I guess the identification is going to be that take 1 and then x1, x2, z, and then y1, y2. And I'm going to identify this with the vector x1, x2, y1, y2. And again, the central direction is going to be the vertical direction. So whenever I say vertical, it really is vertical in this identification. Okay? And so whenever I draw pictures in 3D, or I tend to 5-dimensional, but I'll have hand wave. This is the identification between the group and the room you're sitting in, the integer group. And for now, we're in the discrete world, so in the integer grid in the room you're sitting in. Okay, so this is the setup. Basic properties to keep in mind. All of these are just exercises that you could give to students from the generators and relations. Sorry, from now I should have said, from now on when I write dW, it's going to be the word metric. Okay, corresponding to the generators. How do they call them? A's, A and B? Yeah, so A1, B1, A1, B1, AK, BK. Okay, the C, the central direction, the central element is the commutator, so I don't need to throw it into the generators. This is just to be concrete. The theorems I'm going to be stating have nothing to do with they're independent of the choice of set of generators. So choose your favorite set of generators and look at the word metric on this group. It's going to be the same theorem. It's just going to change constants, which I'm going to be ignoring anyways, and they're going to be irrelevant. So for example, you can just do the matrix multiplication. So what is the metric space? So the metric space for, let's say, for H3 is just you look at the vertices. It's like a graph. It is a graph. The vertices are just the integer grid in the room you're sitting in, and the neighbors of, let's say, X, Y, Z are, right? Look how many neighbors there is. A1, so K is 1 here, so it's A1, B1. There are 2 generators, so the neighbors are multiplied by A1. You have to multiply the matrices and check. It's the same thing. So the neighbors are X plus minus 1, Y, Z. Right. So you can move in the X direction plus 1 or minus 1. You can do also Y plus minus 1. But whenever you do that, you have to add X with the same sign to the Z coordinate. So it has 4 neighbors and the analogous thing in R5. Okay, so maybe I can now very quickly show you just the first picture that I have. So here, this is exactly the Cayley graph that you see. So you look at the integer grid, and there are 2 types of edges. There is adding plus minus 1. This is the red edges. They're just the usual grid edges that we have. But then you have these blue edges, which go in diagonal. They correspond to moving left and right in the y coordinate by plus minus 1. But then there is this twist, which is you add the x coordinate when you add plus 1 to the y coordinate. So you see the blue lines are going in diagonal. And then this is a connected graph, and the shortest path metric is the same as the word metric, and this is the metric space that we'll be interested in. Okay, is this clear to everybody? Everything is really elementary, and I'm gonna and even though the proof happens in the continuous world and they use more machinery to understand the theorem and its applications, everything can be done at this level of generators and relations. Okay, let me go back to my notepad. So let's say some properties that I want you to. So this is really a crash course on Heisenberg geometry. So BW. So whenever I say BR is going to be the ball of radius R. R is an integer centered at the identity at 0. I should have said that in this identification that I had here, the point 0, 0, 0 in R3 is the identity matrix, so it's the identity element of the group. So the first thing I want to say is that the number of elements in a ball of radius R grows like R to the 4 in H5, in H3, and like it's bounded above and below, but up to constants like R to the 6 in H5. So it's one more than the if you just count how many elements are in a ball of radius R in this graph that I showed before, in R3 it grows like R to the 4, even though in Z cube it grows like R 4, and this is R6. The other thing is that if you take any element in the, so let's say, right, I can do it in x1 to xk. It's in any dimension, y1 to yk. And to the left coordinate, to the central element, the vertical direction, you add some integer, m, and ask how far did I move from the original point. Then this behaves again bounded above and below by constants times square root of m. M can be negative. And so this is for every. Okay, so maybe I'll show again a picture. These are very basic things. Both of these things you can prove by induction from these from generators and relations. These are nice exercises to give to students to understand the geometry of this group. But again, let me show you again the picture. I think I explained this is what I wrote. So this is what you see here. So if you want to, let's say, if you look at the left, at the grid at the left, this is the same graph. You're starting from a point and you do the commutator path. This is just you arrive +1 above. That's not very impressive, but as you start going further and further away with the grid, you see that there is some sort of teleportation mechanism happening here, right? I'm doing m steps in the Cayley graph along the edges in the graph, and I'm ending up in the sorry, if I do, what do you want to say? If I want to go, yeah, let's call root of mk. So I do k steps in the Cayley graph, but I end up with vertical displacement in this is k squared. So I did a small number of steps in the Cayley graph, and I ended up very, 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 very far above where I started. So it's like a vertical teleportation mechanism. Okay, is that clear? Let's see. Okay, I'll get this to this later. So this is the picture, and again, and the question that I'm going to be at. So,
are those pictures the geodesics?
Well, it's a Cayley graph, and you mean it's discrete.
Yeah.
So I mean, you want discrete geodesics in a discrete graph, or you're imagining like me the continuous Heisenberg group, and then you're interested about the geodesics.
No, discrete geodesics. I mean, those are the shortest paths between those points.
So the answer is I don't know. Could be what I'm just doing. The first picture here is just a commutator path, which I'm sure is a geodesic. The other one, right? There is a question: is m divisible by 4 or not? There is, I think, there is some arithmetic conditions that will influence whether this is the geodesic or not. But the reason I'm not ever worried about these things is that the theorems and the questions I'm going to get to in the next 20 seconds are independent of the set of generators. So question, is this a geodesic, is a nice question for this, but it's a precise question about your precise choice of generators. But what the nature of the question that I'm going to ask is that it's independent of those arbitrary choices. And therefore, what you see here is a commutator. The first one is the formula that A inverse B inverse AB is equal C. And the other ones are just to do the commutators of A to the m over 4 between A to the power m over 4 and B to the power m over 4. But for that, m has to be divisible by 4. If it's not divisible by 4, then you have to find other there are papers that compute these things exactly for this set of generators. But there are somehow they go in a direction which is not the direction that we're going to be interested in here, because they are about this set of generators. Okay, so things like what is a geodesic in all of these things are, in all of the questions we're going to get to, are very interesting, but not for the topic of this talk. Okay. Okay. So I introduced to you the object that we're looking at, and the question that I'm going to be interested in, and I arrived at it from an application, and actually formulating the question took 10 years. So in coming up, I think formulating the question is a big part of the answer I'm going to get to. But the question that I'm asking is the following. So you're looking at Z cubed, this integer grid, which I'm identifying with H cubed, and the same thing will happen in H5. And I'm giving you some set. Let's say it's a finite subset. Okay. Very soon we're going to move to R cubed, and it's going to be a measurable subset, compact measurable, so called compact set. Let me draw it with my block. Now, let's look at the edge boundary of the set A in this infinite graph of the integer grid. So the edge boundary is just the points that are in A, which have an edge in the graph, one of those edges that I drew, leaving A. So one endpoint is in A, the other endpoint is not in A. So right, one of them was the X, or there could be this diagonal. I don't have colors with my pen, but the blue and those red edges, the two types of edges. So let's look at the edge boundary of A. Okay. And suppose it is a small number. I'm not telling you it in a qualitative, like I will quantify this in a second, and how to quantify it is really the question. But suppose I told you here's a set A. Here's a set A, and it has a small edge boundary. So it's difficult to leave A in the horizontal directions. The vertical direction is literally the vertical direction, the Z coordinate. And I call the other generators, in this case A and B, in H5 it's A1, A2, B1, B2. I call the rest of the directions the horizontal directions. Okay, when we take the limit, this will be those horizontal vector fields that we will get to in a second. Okay, so I suppose I tell you it's difficult to leave A in the horizontal direction, in the sense that the edge boundary, just counting how many edges have one vertex in A, edging of the Cayley graph, and another vertex, not in A, and the other end of the edge, not in A, there's a small number of those. Okay. So if it's difficult to leave A in the horizontal direction, in the direction of these blue and red edges, then formally, just from the presentation, it means that it's also difficult to, so I'll denote it. So DHA is just going to be all the X, Y, Z in A, such that such that let me erase. Such that one of these edges, X plus minus 1, Y, Z, is not in A, or the other types of edge, or X, Y plus minus 1, Z plus minus X is not in A. So you start in A, and one of these edges is not in A. So if DH, the number of, I'm counting how many of these edges are there, is small, then just from the presentation, this implies, and I have to, so this means it is difficult to leave A in the direction of the edges. This implies that it is difficult, whatever that means, to leave A, to start from a point of A in the vertical direction. So leaving A in the vertical direction means starting with a point in A and finding a point which differs only in the Z coordinate, either above it or below it, which is not in A. Now, why is that? That's just because the vertical direction is the commutator of horizontal direction. So so you just look at the path, one of those paths that I drew, starting from the point in A to the point outside A. This path consists only of horizontal edges. So at some point you have to depart from the set in the horizontal direction. So for every transition, vertical transition, from a point in A to a point straight above it, there corresponds a horizontal transition from a point in A to a point outside. Is that clear to everybody? This is very, very quantitative. Okay. The question is, how do we quantify this? How can we quantify this? Okay, and the way, so again, I'm going to write down the answer, and then I'll show you what it's good for. But many of you will have other guesses, and a big part. I'm not saying that the complicated, little bit complicated answer that I'm going to show is not self-evident. It's not like you would wake up in the morning and say, yes, obviously this is the answer. This is something which, it's true, but I'm not claiming that you should say, oh yeah, obviously this is the way it should be. So I want to quantify this phenomenon in this very concrete graph, this matrix set or R3 or whatever. So the way to do it is we look at vertical perimeter. At distance T. So I know this is like the vertical perimeter at distance T. The vertical boundary at distance T of A, it's very similar. It's all the points X, Y, Z in A, such that X, Y, Z, either plus T or minus T, is not in A. Okay, so this is exactly this picture that I said take a point in A, and then this is distance T directly above it, and you left it. Okay, so I'm going to be counting how many of these transitions there are, and here is the theorem, which is answering the conjecture. This is answering a conjecture that they made a decade before for an application that I will show you in a second. So, and this is two theorem. So, so this is myself and Robert Young, and one of them is 2017. That's what in dimension 5 and above, and then 2020 and is the three-dimensional. So I'm going to start in dimension 5 and above. So one, so for every A in Z to the 5, okay, so which I identify with H5, and but it's really I can do H to K plus 1 for any K at least 2, and we will see what's happening. Okay, but let's focus on 5 dimensions. You do the following thing. Look at the vertical boundary distance T. Okay, so this is the number of the size of the set here. Okay. Count how many of these transitions there are, but square the count, normalize by T squared. This is when this is dictated by scaling there again. So there's a correct normalization. Then sum from T goes from 1 to infinity. Take the square root. So this is some way to bookkeeping. This is how you count how many vertical transitions there are. This is at most a universal constant, 100. I don't know what constant we get. Whenever I write lesser into this table, I just mean some universal constant. And then you just look at the horizontal boundary. Okay. Okay, so if the right-hand side is small, there are a small number of edges leaving the set. Then there is a small number of vertical transitions. But you count these vertical transitions using this funny thing of counting, squaring the counts, and the normalization is forced on you by scaling variance. If I told you it has to be the sum of squares and then normalize in some way, you could reverse engineer that you need to divide by T squared if you just look at the symmetries of the problem. Okay, so the important thing is it will behave like sum of squares. Okay, so is the inequality clear? And 2 is optimal. So yeah, I mean, I'll say in a second. So this is this 2017 result. 2017. And the proof in a very subtle way breaks down for dimension when you go below dimension 5. And it took a while, and we had to invent. This was something completely unexpected. And it was, I'll show you later why. I'll convince you that why it was so completely unexpected. But if you look at that cube, so really the integer grid in the 3-dimensional room that you are sitting in, and for which I will be able to draw pictures, show pictures in a second. So for every subset A in Z cubed, and again, this is H cubed. I want to do a similar inequality. You do this count, but the correct exponent, the best exponent you can put here is power 4. And then this forces a T cubed in the denominator on you. Okay, so when I say best exponent, this is a little exercise that you do. This is really exercise, again, generators and relations. If you have any inequality of the form, what happened? Of the form dV A to the power P, let's say, and then the correct power of P, which I think should be P over 2 plus 1. any inequality of this form, okay, which is all the inequalities that I'm talking about here, they become easier as p increases. So you're always asking what is the smallest possible p for this inequality to hold. So if I told you this inequality holds for every set A with p, and you have some p prime bigger than p, then formally you can deduce by playing around with the generators in relation the same inequalities for p prime, which is bigger than p. So the game is in all of these things, just so you know, the enemy is to find the smallest possible exponent for which it holds, and you need to find the smallest possible exponent. I'll show you in a second one of them. There are actually many applications. I'll show you one of them. Okay. So this is the theorem.
Is p always integer?
No. For any well, in this particular case, it's p is only 2 or 4. But I'm saying that these inequalities, if you know this inequality with power 2, then you know it also with power 2.001 or 3. So when I'm saying this is the best possible inequality, I'm saying you cannot do this with power 2 changing to 1.99999. 2 is the best exponent, and 4 is the best exponent for the first Heisenberg group in this isoperimetric inequality. But this answers the question, this group theoretic or this combinatorial question, and we'll see in a second what is the functional version of these things. This answers the question, how do you quantify this phenomenon that if it's difficult to leave a set in the horizontal direction, in the direction of one of the generators, then it's also difficult to leave the set in the direction of the center, the vertical direction, which is the commutators of the generators. Am I clear that this answers it in a short way, and maybe not an obvious way to guess a priori, but this is the truth, okay? Is this clear? So this difference between 2 and 4, and between dimension 5 and dimension 3, was a real shock to me. I mean, I conjectured this inequality in 2010, so a while ago, but I conjectured that the first inequality with power 2 holds for all dimensions, and we'll see in a second why I conjectured that. So you can call this both as a positive and a negative answer to a conjecture like this theorem. Okay, so, but the fact that the answer is negative in dimension 3 and positive in dimension 5 has applications, but which I might get to. So when this unexpected behavior between the dimensions was really unexpected, and I will show you in a second why. But that's good, because that led to applications that, of course, I didn't expect them because I didn't believe that this would be different happens. Okay. So is the theorem clear?
Yes, but Dan Strook asked, how does the constant depend upon p?
Also, when I say increasing, I mean of the constant. So if you have this inequality with constant k, and then you have p prime bigger than p, then the inequality holds with constant p prime. And sorry, with p prime and k changes to a universal constant times k. I don't know, 2 times k, maybe 10 times k. This is kind of depends on the choice of generator, so I didn't. But it's 10. Let's say I'm sure that factor 10 is fine. Okay. So if you know it's power 2, then you know with power 2.001 or power a million, and the constants change by a factor k 10. But and this factor is just an artifact of your choice of generators. Okay. So the only reason I mentioned this is just that you should keep in mind, as we thought, that always in these things, the game is what is the smallest exponent in these isoperimetric inequalities. What is the smallest exponent in the left-hand side of the counts that we see here, the vertical transition counts. Okay, so as you notice, I did not get to the continuous world. We'll get this there in a second, but it's extremely elementary. The proof is not elementary because I think in the continuous world, but the applications will be in the discrete world. But not all applications. The applications that I'm going to show to a very, very major question in computer science. But is the theorem clear? It's two theorems, and there is a difference in the and one of my goals here is to convince you that there is a reason for this difference. Okay, so I'm wondering what I should do first. Should I first show you an example? There are many applications of this, or I should first explain what goes into the proof. Maybe because this is I will derive the application in the end and first jump into the proof, unless people are more curious, the audience is more curious of first thing the application, and then maybe we'll see less of the proof. And just just make a choice. I plan to do both, given that I might run out of time. I think, should I jump into the proof, or of course I'm not going to show the details. I'm just going to explain the cast of characters or what goes in, and then at the end arrive at one of the applications. That's what I'm proposing to do, but I can also flip the order. Is there a preference in the audience? If nobody says anything, I'll do it, but I'll get to the proof first, because I'm a mathematician. I want to see a proof. But maybe people are interested in how is this related to computer science, and that is also something that I'm happy to indicate. Is there a preference?
We'd like to see both.
Of course, the question is obviously first, given that there is a chance that I intend to show both. But if I'm going to run out of time, what are you willing to risk seeing less of? Okay, maybe I should
show the application first.
Really? Okay. Okay, I'm sorry. This is the opposite of my instinct, but I'm happy to do it. Okay, so very quick. Okay, so quick application, and then I'll show the proof and try to convince you what is the difference between dimension 3 and 5. Of course, there are differences between dimension 3 and 5, but the differences here are something subtle and surprising. It's not just it's not growth rate. It's really dimension 3 and dimension 5 and above, and there is something very subtle that leads to this difference. Okay, so as I said, there are many theorems that we show you in one application. So first of all, there is isoperimetric inequalities usually have a functional form. I don't know this is here. This is the kind of thing that he does a lot, and of course I learned a lot from him. I can restate. So there is an equivalent formulation. Functional formulation. So again, in the discrete world, I'll flash a slide. What is the continuous inequality with just point-correct inequality? Some Sobolev embedding. There is a continuous version of this, which is really how it thinks. So if you have a function f from, let's start z cubed. There's an analog of this for z5 to r. Then you do the following. You look at some t goes from 1 to infinity, and then you do the following. You look at f of x, y, z plus t minus f of x, y, z. What did I do? I did not intend to do that. Sum this over all x, y, z in the integer grid. So suppose f is finitely supported. Square the sum, normalized by the t squared. Sorry, in this case it did h3, so 4 in this case. Then the power is 3. And that's less than sum x, y, z in z cubed. Then you look at f of, again, now the edge is x plus 1, y, z minus f of x, y, z. And there's the other edge, plus f of x, y plus 1, plus, and plus minus, it doesn't matter. Z plus minus x. Okay, so this is the same inequality. If you look F to be the indicator of a set, then the right-hand side is precisely these differences, these absolute values of a 0, 1 valued function. It's just counting how many times it's 0 or 1. So this is precisely the horizontal transitions. The left-hand side is precisely the vertical that counts raised to the power of 4. And there's in H5, in dimension 5, there's an analog, or the obvious analog. So when F is an indicator of a set, what's that mean? So when F is the indicator of the set, this just coincides with the previous inequality. And then there's the co-area formula. For those who know, there is an argument showing that indicators of sets are the worst possible. So you can get you get the functional version. Okay, so that's the functional version. And then obviously, so in Z to the power 5, the power 4 here will become 2. And the denominator will be. Is that clear? This is really the functional version. And then there's also there's another equivalent formulation. You can make this a finite inequality, and that's what I need for the finite inequality. It is equivalent is the following. So instead of looking at these infinite sums, I want to sum them on a ball of radius and in the word metric. So it's how is it? So you look at the sum, maybe x in a ball of radius n, and now you look again 1 over n cubed, 1 over, sorry. And now you look again. Okay, so you look at the sum, scales going from 1 to n squared, and now you look at 1 over t cubed, and now you look at this count, sum x in the ball of radius n, and now you look at f of x times the central element to the t. This is just adding t to the z coordinate minus f at x. This sum you raise to the power 4. Take the 4th root, and that's less than the sum x in a ball of radius. I just need the universal constant times, and 100 is safe. But I don't know what the best constant is, depending on the generators. And then you have f of xa minus f of x plus f of x. Okay, so the only difference between this inequality, the infinite inequality over all the points, is that I made it a finite. This is, you look at the ball of radius n in the word metric, right? And that was b sub r was the ball of radius r in the word metric, and you just sum over x points in this finite set, and then the right hand side is like discrete Sobolev norm. You need to sum over x in the ball, which is a little bigger. The universal, the radius is numerator factor. Probably factor 10 is enough. The factors just depend on the generating set. Okay, so all of this is equivalent. It takes a few pages to prove all these equivalents, but these are partitions of unity, all kinds of things like that. This is kind of things that are understood. Okay, so these are all equivalent statements. The isoperimetric inequality is equivalent to these functional inequalities. So once you have the functional inequality, again, still equivalent. These are all equivalences. And it says, now we take f from h from z cubed to any L1 space. So let's say little L1. It doesn't really matter. So look at the infinite sequence space with the L1 norm, and then I'm going to write the same inequality. So this holds, but instead of absolute values, I'm going to take the L1 norm. So this is a function taking values in infinite dimensional L1 space. And the reason this is equivalent is, well, of course, one direction is obvious. You can take off the function can take values in a line, in the real line. And conversely, convexity just helps you. So you write down the inequality. A function into L1 is just an infinite sequence of functions going into the real line. You write down the real value inequality for each one of them, sum them up, and at some point there is some convexity related of these quantities here. And you can trust me. No, I mean, don't trust me. Convexity helps you. If you sum all of the inequalities, example, you use triangle inequality in L4 or something, then you get the inequality that we wanted in the infinite dimensional inequality. Okay, so this was, of course, and I wanted this inequality here. But it was designed to tensorize easily. Okay, so to get a dimension independent or an infinite an inequality of functions taking values in infinite dimensions. And instead of little L1, you can take any L1 and any measure space. Okay. So is it clear? So these are all equivalence formulations, and all of these things are exercises. The inequality wants to be infinite dimensional. It's been invented to tensorize in an easy way. You have to just check it. Is this clear? Okay, so now I claim that this shows that the geometry of the Heisenberg group is highly incompatible with the geometry of L1. So I claim that the biellipsis. Now I'm interested in the biellipsis distortion. Of, let's say, H3 and H5, or of balls in an L1 space. So what do I mean by that? So suppose, let's start with H3. So you have F from H3 to L1, or any L1 satisfies this. So f of x minus f of y in L1 is always at least the word distance between x and y, and at most some number d times the word distance between x and y. So you succeeded to a psi. This is for every 2 points in the ball of radius n. Okay, so suppose you look at the ball of radius n with the word metric, and suppose you could represent any vertex of this, any element of this group, or any point in Z cubed as a function, as a sequence, as an element in the infinite dimensional sequence space, in such a way that the word distance between in 2 points is up to this factor d, capital D, which is called the distortion, just the L1 distance, the sum of absolute values of distance, of differences. This is a major simplification of the metric in L1. So suppose you could do that. Then I claim D must be very large. So let's see why this is. So let's look at the inequality here. Maybe I'll rewrite it. So let's copy it. Let's say what was it in f of xa minus f of x. These were just the generators. Okay, so let's just see what this means. So because if I use the upper bound, I just very easily just I'll use the upper bound. So each of these terms, the distance between xa, and x in the group is 1. That's the definition of the word metric. But this is bound from above by d times the word distance. So what's written here is less than d times the number of elements in the ball of 100n, and I told you this number of elements this behaves like d times n to the 4. Okay. At the same time, if I look at the lower bound, the word distance between x and x when you add the t to the z coordinate is root of t, is the root of t. This is this commutator relation. So each element here is at least root of t. There's a constant. It's a twiddle. So if we write all of this together, we have the sum. T goes from 1 to n squared, 1 over t cubed. Each of these elements is root of t. This root of t had, so what you have here is the number of elements in the ball of radius n, which behaves like n to the 4th. And then there is a root of t. All of this is raised to the 4th, and all of this is the 4th root. And if I copied correctly, so what's going on here? Root of t to the 4th is squared, so we have sum of 1 over t. We got this harmonic sum. N to the 4th, but there's a 4th root. Is this n to the 4th? So if I compare n to the 4th cancelled, and we get that d is at least 4th root of log n. So there is no way to represent the points in the Heisenberg group as points in an L1 space, in a commutative L1 space. You have to pay a price of 4th root of log n. And in the paper, we show that this is sharp. So we just built an embedding that does this. So, so the theorem, which is a corollary, is that the by Lipschitz distortion, the smallest possible d of Bn in H3 is bound above and below by universal constant multiples of 4th root of log n, and the same thing for Bn in H5 and up. If you do the same computation, you get just a square root of log n. Okay, so finding, okay, yeah, I see them. So this is a finite set, finite graph, which we showed cannot be represented as points in L1. Okay. Now, this is related to something called the Goldman-Zimmer conjecture. And yeah, I'm probably going to show mainly the application, then go very quickly through the pictures in the slides to explain what I do in the proof, sadly. And so the Goldman-Zimmer conjecture is an absolutely, it relates to an absolutely fundamental question in algorithms. So there's something called the Sparse Sculptor problem. I don't really know how many computer people who know the background of this are in the audience. Okay, probably not many. So the Sparse Sculptor problem is a problem in about finite sets. It's something that is used in algorithms left and right. It's a very, very useful question. So you have some finite sets, let's say the numbers 1 to n, and you're given two matrices, Cij. This is a symmetric matrix with non-negative entries, and Dij. So these are called, never mind why, we'll use in a second. They're called capacities. And these are demands. Right, so you have this universe of n elements. This is I, this is j, and I and j have a capacity associated with them, so a negative number, and also a demand associated with them. Okay, and the goal is to compute or evaluate the following. It is just an isoperimetric discrete, a general discrete isoperimetric problem. What you do is you look at so you look at the minimum over all the subsets of the universe, proper subsets, so it's not empty and not everything. And what you do is you look at some i's in S, j is not in S, Cij. So this is the capacity. So if this is the subset, you look at what is the total capacity crossing the boundary. One is intersecting, the other one is not. So S is here. This is the left-hand side of this section. And you divide this by the demand, the ratio of the total capacity crossing the boundary. Yeah. And by so this is okay problem specific already. When you have to for various problems you have notions of boundary. CIJ is just a general notion of a boundary of the set. DIJ is some sort of count of how big each side is, and you want to partition your universe into a piece which has two pieces which has that have the smallest interaction between the two sides in this weighted way, and the weights you cook up based on an application. So there's, if those of you, I'm not going to get to it, there's a book of Schmoy's called something like Sparse Sculptor and divide and conquer algorithms or something like this. This is whenever you have an algorithmic problem which you want to solve by induction, take your universe, you want to partition it into two smaller pieces, and solve the problem of the two smaller pieces, then glue the solutions. One of the standard ways is to set up an induction like this is to solve this partitioning problem. So this is extremely general and extremely useful. It's called the Sparse Sculptor problem. So old and general, and it's been studied a lot, but somehow the field got stuck in the mid-90s. So Gomez and Lineal in 1995, roughly, maybe in 1997, I don't remember exactly, proposed an algorithm for Sparse Sculptor called the Gomez linear semi-definite program. They didn't know how to analyze it, but they conjectured, which is today it's the best known algorithm. I'm not saying that they didn't know there would be a better one, but nobody proposed. No, we simply don't have an idea yet. You can artificially invent algorithms, but like a masochist, we don't know how to analyze them because we go over the proofs and we just invent an algorithm which foils that proof. But it's really the best known algorithm, and it took 20 years, more than 20 years, to figure out what this algorithm does. And using the H5 result that I told you, and that's so the central point. The capacities and demands are the capacities are supported on the edges of the Heisenberg proof, and the demands are numbers which come from a duality argument. I can prove they exist. We can prove the theorem, and this is many years of work, but we get that this algorithm, which I didn't tell you what it is, the Gomez linear algorithm for Sparse Sculptor must sometimes make an error of universal constant times root log n, and earlier this is Aurora Leoni, back in 2005, I'm guessing, something like that. It always succeeds. To find a set S that is a minimizer that is big O of root log of log n. There's little O terms. That is big O from the minimum. So I'm trying to find the best way to partition my universe so that I minimize this function. We could prove that the algorithm finds such a partition, which isn't the absolute minimum, it's just the minimum up to a factor of root log n. up to little O terms. And the Heisenberg is right now the only example I know, and there's a reason why we arrived at the Heisenberg group. But this theorem that I showed, the isoperimetric inequality, shows that it sometimes must make an error of this size. So this solves the problem. So there's an algorithm that has been proposed in 1995 and has been studied by many, many people. And it's present only through the Heisenberg group and really ideas in group theory and analysis and geometric measure theory. It's present, and we can understand how it performs only going through this picture. So I am 6 minutes over time. I took a lot of time to introduce the group, and I did not get to the proof. So I know people probably want to go. I have a bunch of slides which show pictures of what goes into the proof of these isoperimetric inequalities. I'm happy to show them only if there's interest, but I don't want to keep anybody captive. So if there's anybody here who wants to ask a question, maybe and leave, then let me know, and then I'll switch to the slides that I have and explain really with handwriting, not handwriting, but in terms of ideas, what kind of objects go into the proof. So just to give you a tease, the surfaces of this form, some fractal surfaces in 3D would come in, but I will do it only if there's interest. So how about I ask questions now for those who want to leave, and then I'm happy to stay for those who want to stay and explain how I prove the isoperimetric inequalities. Is this a good plan, Arthur?
Yes, this is great. And I want to first thank you for a very interesting talk, introducing us to some unusual ideas with unusual phenomena. So I'd like to applaud this talk that you gave and open the door for questions. And I hope when people ask questions now, they'll turn on their video so we can see your face and talk face to face. So should I leave your slides showing while we have the questions, or should we just look at the faces? I think we can leave the slide.
If the answer will require me to draw, then it's a good idea to leave it, but it's up to you.
Yeah, let's leave it for the time being. And who has the first question? Kaifeng, you have.
Oh yeah. So here the inequalities about the vertex isoperimetry is also true for edge isoperimetry inequality.
The edge isoperimetry, this inequality was relating the edge isoperimetry to the vertical, the vertical. So I don't understand the edge isoperimeter. The edge isoperimeter was already in the inequality. So what is the thing that you want differently?
Yeah.
But what is it? It's only the inequality has the edge boundary in it. Where is the inequality? Here. So what do you want different?
So I mean, the distance is about the vertex distance or about the edge distance?
This is the edge boundary in both cases. So you want what? You want to bound from above the edge boundary?
Yeah.
That's unnatural. So the answer is no. I mean, there is no way to bound. You cannot bound. If it's difficult to leave a set vertically, it doesn't mean anything about the edge boundary. You can take just a coset of the center. Take a vertical line, the z-axis. Then the left-hand side is 0. Right? A point in it. If you take a point in it, then a point above or below it is still in it. But there are clearly edges, many edges leaving the set. So you can never bound the left-hand side by the right-hand side. It's the only direction that you can go.
Oh, I see.
And the left-hand side vanishes whenever your set is a union of cosets of the center, a union of vertical lines. Okay, while the right-hand side is never 0 unless your set there's always you always leave the set unless the set is everything, all of our of Z cube. So there's no way to reverse this inequality.
Oh, I see. And also, is there a way like to write this discrete derivative by some its Fourier coefficient, like the Boolean function?
Fourier coefficient. I do not. So this is there is a quadratic version. So this inequality, right?
Mm-hmm.
The inequality. I wrote the functional version of the inequality here. Probably I should show on the other file, the slide. I have it written. It's a strange inequality. It's an L4 of the internal sum here is an L1 sum.
Mm-hmm.
So that's it. So it's an L4 of L1. There's a version for LP. When P equals 2, when it becomes quadratic,
Mm-hmm.
then the way I know how to prove this inequality is using the representation theory of the Heisenberg group. So that's what we mean Fourier analytic, I guess. But the minute you move away from the quadratic inequality, I do not know how to use Fourier analysis to prove it. There is a representation theory. I mean, there's no way to relate it to the irreducibles of the Heisenberg group. The way I don't see how. So the proof really does not go through representation theory. In the other endpoint, which I didn't write it, the L2 inequality, it definitely does.
Mm-hmm.
At the end, typically L1, the endpoint inequalities of these like Sobolev-type inequalities usually do not come from Fourier analysis. They come from geometric measure theory, some structural information about how boundaries of sets look. And this is what we do. But in the gut of the proof, there's lemmas which use the quadratic inequality, which is representation theory in the gut. So, but it's not. But it's more than just Fourier analysis or representation theory. Okay? But I'm not saying there isn't steps in the proof which use Fourier analysis, but there's steps in there. They're a small part of the proof. They're not the whole proof.
So could you show us some pictures that illustrate how these inequalities arise?
Yes. Yeah. That was my instinct before. So okay, let me skip. So this is just the introduction of everything. The pictures in my mind and the proof and everything, and that's the way I think, and that's where I come from. I'm not a discrete person, I'm a continuous person. I want to switch to the continuous world, okay? So just, again, very quickly, you see on the left here, the integer grid. Right, there's these edges of this discrete graph, the discrete group. So there are the blue and red edges. So you can, so let me explain to you what is the Heisenberg, the continuous Heisenberg group is the Carnot-Theodori metric, okay? So first of all, actually, to simplify life, you can look at the integer grid with this discrete, this just word metric. There's nothing special, it's a graph. But now multiply the integer grid by epsilon, small number. So and this is a metric space, and take the limit of these metric spaces in whatever meaning that is, Gromov-Hausdorff limit. As epsilon goes to 0, and that will be a metric on R3 or R5 if you're R5, and that's the Carnot-Theodori metric. So I really don't have to define it, but for those of you who just want to know how this relates to what is the Riemannian or sub-Riemannian structure, what you do is at every point there is the blue edge and the red edge. So it's in 3D. There is a two-dimensional plane spanned by the red and blue edges. This is the middle picture. Okay, and then the commutator path that you see that I drew. I'm showing how the plane moves as you go along the commutator path, and in the limits you look at you have this field of two-dimensional planes in R3, and the Riemannian structure is that you look at all paths joining points whose tangent at every point is belongs to this two-dimensional plane that I draw here, and you look at the shortest path metric with this additional restriction that the tangents belong to the two-dimensional plane. In R5, it's going to be in a four-dimensional plane within R5. Okay, so that will be the analog. But if you don't want to know the Riemannian structure, just think about the limit of these discrete objects when you multiply every edge by epsilon. Okay, and let epsilon go to 0. And the limit is in Gromov-Hausdorff sense. Okay. So the metric on R3 or R5 that we get here, I'll call H sub 3 sub R, and CC stands for Carnot-Theodori metric. Okay, but it's just the limit of these discrete metrics when you multiply each edge by epsilon. Is that clear? Okay, I'm going. We're in the continuous world. There's a house of dimension. So what happened to this rate of growth is that in R3, the dimension of this metric is the house of dimension is 4. and H5 is going to be analogous, and the house of dimension is 6. And now the analog of these vertical perimeters is what I wrote here. Just now, you look at, you have let's say a compact subset of R3, and instead of counting how many points are in A and you add plus minus t to the z coordinate, you leave A, you look now at the volume, the 3-dimensional volume, the big measure of all the points in A, such that if you add plus or minus t to the z coordinate, you leave A. So now what was counts before becomes volume. Okay? I just want to explain the setup in the continuous world. And then these are the same inequalities in the continuous world. So you have these 4th powers of the volumes, or in dimension 5, the squares of these volumes. This corresponded to take the counts of points and raising them to the correct power. The right-hand side, which was the perimeter and the horizontal boundary, just becomes the house of measure in codimension 1. So remember, in R3, the house of measure was 4 of all of R3. So I take codimension 1, which is a 3-dimensional house of measure of the boundary of the set. Okay, and these are the same inequalities I can put formally if one implies the other. So they're really the same thing. It's just a continuous version of the same discrete phenomenon. It's clear to everybody, or? Of course, I didn't explain the derivation, but the derivation is not where the ideas lie. Okay? So this is what I want to prove. I want to somehow control the vertical boundaries, volumes, by house of measure of the boundary. Okay, and this is the power 2, 4 are written for you here. And this is the functional formulation. So, if you look at the left-hand side, or the top row, is that you have a function to the real line, and you look at f of x, y, z, and you add t minus f of x, y, z. You look at the absolute value, you normalize by root t. Raises to the power of 4, dt over 2. So together it's dt over t squared. And that's bounded by this Sobolev norm, which is the f dx. That corresponds to the plus minus 1s in the x coordinate. But the infinitesimal version of this blue diagonal edges is the f dy plus x df. So this is the theorem I wrote here, the Sobolev inequality, is equivalent to the initial inequality. And the funny thing is that this is an L4 of L1 inequality. That's the best you can hope for, and that's the truth, and that gives the correct connection between Heisenberg geometry and commutative L1 geometry. Okay, so this is just a continuous version of what I said, and that's where I'm going to be thinking. Okay, so let's get to pictures. Okay, this is the LP version. Let me skip the one. It's a big. There is an LP version, which is the analog of this, which Vincent Laforgue and I proved earlier. And the funny thing about all of this is that the LP version, there is no, in the LP world, there is no difference between dimensions 3 and 5. It's only the endpoint case when p goes to 1 that the power 2 becomes a power 4. So this is it's like a jump discontinuity which is unexpected, which occurs in dimension 3 but not in dimension 5. The LP version is something which ignores the dimension of the underlying Heisenberg group. Related to the question of Chi-Fund, p equals 2 in this inequality. Look what happens. So 2 over p, the power 2 over p becomes 1 in this theorem of Laforgue and I. And power 2 is a square. Right? Oh, I can draw on this. This is great. I didn't know. So for p equals 2, this is an honest quadratic inequality. Both sides are quadratic. And if I hand you a quadratic inequality, then you can decompose it to irreducibles and see what happens and prove it for every irreducible the representation theory of the Heisenberg group is known. That is what you meant by the Fourier analysis. And just check it one by one, and it becomes elementary inequalities, and you can prove it like that. But I'm interested in p equals 1, and I have no idea how to use a representation theory. I will do something geometric. Okay. This is the dimension 5 version of this. Let me skip. Okay. So oh, my microphone fell. Give me a second. So the idea is something called a corona decomposition. It's in reference to Carlson's corona theorem, but this is something that has been invented by David and Sens in the 90s, and it's a very, very powerful philosophy in geometric measure theory and Fourier analysis. But in order to explain how so what I'm going to show is, I'm going to show you a structure theorem with pictures for what do surfaces in R3 or R5 look like. They can be decomposed to simpler pieces. But one of these pieces are graphs of Lipschitz functions. But in order to do this is to define you have to redefine the notion of what it means to be even a graph of a function. So there's a notion of a non-commutative graph of a function that will show up. And this was luckily, this is roughly when I asked this question, the Italian school, Franchi Serapioni and Sarah Casano, have been developing this just because they were interested in the geometry of the Heisenberg group. So this was very, very lucky that this was developed independently for us. So let me, so maybe if I told, now let's look at R3 in our room. Suppose I gave you a surface in R3, and I'm asking, is this a graph of a Lipschitz function? Okay, so one nice exercise again for students. Here's one way to characterize being a graph of a Lipschitz function. I don't know, maybe many of you have seen this. So a graph of a function is a graph of a Lipschitz function. If look at the double cone with angle theta, so that's drawn here, and put the cusp of it on the graph, and then draw the picture that you see here. So look at all double cones. Right? So a graph of a function is a graph of a Lipschitz function if there exists some positive theta, such that all of these double cones meet the graph only at its apex. So you can find a small enough angle so that when you draw these double cones with the apex on the graph, the rest of these double cones don't touch the graph. That's a nice exercise. That's what it means to be a graph.
That's if you said this is a quantum notion. I don't.
This is a commutative. This is an Rn, the usual Rn. This is what it means to be a graph of a Lipschitz function, R3. Okay, so look at the, let's look at in R3, everybody sees.
Is there a quantum version of this?
Yeah, in a second I'll show it. Yeah, in a second I'll show it. So look at Arthur's room. You're using non-quantum R3, right? In Euclidean R3. And on your left, I see a nice bookcase. Think of this now. Think of this as, let's say, the YZ plane. And look at the boundary of the books is going to be a graph over the YZ plane on your left, and it's actually on your right, but it looks to the rest of us on your left, Arthur. So you can look on your right at the bookcase. These books, the boundaries of these books, think of it as a two-dimensional surface. And in Euclidean geometry, this is a surface of a Lipschitz function. If you can come up with a definite positive theta, such that all these double cusps, so you put them on the edge of the book and you look at the double cusps, it will only touch the double cone, it will only touch the surface at the cusp. This is commutative, nothing is quantum. These are R3 Euclidean geometry. Okay, nice exercise in Euclidean geometry. Now I want to discuss the Heisenberg version of this. And for that, I have to change what the notion of a graph is first. What did I do? So there's a notion of an intrinsic graph. So, so a graph is a function from a two-dimensional plane to R. The two-dimensional plane is going to be the vertical wall, the YZ plane, to the left of Arthur or to the right of Arthur. If you look, the wall on your right, Arthur. Okay, so imagine this is the YZ plane, all the X in R3 in your room, from which the Y, the X2 coordinate vanishes. Okay, and you have a function from this to the real line. Okay, if I would ask you, Arthur, what is a graph of a function? In the usual commutative world, you would say, take a point on your wall in V, and now look at its value. So look at the point U, look at f of u, and just look at u plus 0, f of u, 0. That would be the graph of the function, right? The point above u, you just go in the remaining direction, which is the y direction. Yeah. you just add to it, right? It's the point above u is that you just add f of u to the y coordinate. I believe that it's the xz plane, and the graph is just like a curtain, or the boundary of the bookshelf. And is my analogy clear? And tell me if I'm confusing you by using this. So that's how you define a commutative graph. An intrinsic Lipschitz graph is the same thing, except that you do multiplication, matrix multiplication. So it's, you take a point u, which is in this identification between points in R3 in the plane Z, and you multiply it by the point 0 f of u0. But the multiplication is now non-commutative. Instead of addition, which is commutative, the operation in R3, you multiply. So that is the graph of f in the non-commutative sense. We want to call it quantum Heisenberg sense, the intrinsic Lipschitz graph. So if you want to be concrete, f is defined on the plane x0z, and its graph using the multiplication, matrix of multiplication, is all the points of the form x, f of xz, z plus x of f of xz. That's a graph of a function in the Heisenberg, the intrinsic graph of a function. So I'm changing the definition of what a graph, an intrinsic graph is. But it's natural. It's the same thing with addition would be the usual notion of a graph that we're used to in our familiar Euclidean world. This is very important. So tell me if I confuse anybody by using this analogy of the wall in Arthur's room. There's another advantage of some not Zoom. I usually, when I give a talk about this, there is actually an actual curtain in the room, and I can actually explain by pointing to it. But now I have to refer to Arthur's room. Okay, but is that okay?
Oh, that's okay.
Yeah. Okay, so that's a graph of a function. And then there's the intrinsic Lipschitz condition, and I wrote it down here. So the graph is intrinsic Lipschitz if there's a number lambda between 0 and 1, such that for any 2 points on the graph, this is the left-hand side here, these are generic points in the graph. U times 0 fu0 and v times 0 fv0. The distance between fu and fv is at most this limit of this word metric, the Carnot-Cartan metric, between the points in the graph times lambda. In RD, in R3, the whole thing is generalized to RK. If you write the same condition and you write Euclidean metric, then you can square everything and simplify, and you get the usual Lipschitz condition. But this becomes actually a very nice and subtle notion of the Lipschitz condition. Let me tell you what it means geometrically. So remember, this was the picture of a Euclidean Lipschitz graph. A graph is Lipschitz in the Euclidean world if there's a definite theta positive, if there's a definite positive theta, so that when you draw the double cones with apex on the graph, they only touch the graph at that point. So now what we're going to do, we're going to do Heisenberg cones. So Heisenberg cone has this, departs from its cusp quadratically rather than linearly. So I wrote a definition, but this is the analog. This is, if instead of Carnot-Cartan metric, you wrote Euclidean metric, this would be a double cone. But because of this square root behavior that I wrote, the cusp here, this graph departs from its cusp, this double cone departs from its cusp much faster, quadratically rather than linear. So, and then I want the same picture. So instead of this, I do this. I want at every point I do a Heisenberg cone, which is a cone that departs very quickly from its cusp, and I want that to not touch the graph anywhere but the cusp, the apex. Is that clear?
Yeah.
But you do it, and so you do two things. First of all, you use Heisenberg cones, but you also change the definition of what a graph is. You don't do it for the graph of the function in the usual sense that we talk about. You do it for the intrinsic graph in the sense of this matrix multiplication. So I changed both what a graph is and what the Lipschitz condition is.
Yeah, and you use this picture to motivate the proof.
Yeah, so this is what, so because it's hard, because now it's easier to leave the graph
Yeah.
using the double cone, intrinsic Lipschitz graphs become monsters. They become fractal objects that can have Hausdorff dimension bigger than, well, this is a two-dimensional plane. In R3, the Hausdorff dimension can be bigger than 2, for example, even though they're intrinsic Lipschitz. So this is an example of what an intrinsic Lipschitz graph in R3 looks like. Mm-hmm. Okay. And there's of course an analog in R5. I just can't draw the picture, but they're worse. So intrinsic Lipschitz graphs, they're worse. They're good. When you do these analogies, you get objects which are not nice curtains, which are smooth curtains. They're actually fractal objects, but they're the right generalization of the concept. Okay,
so that's really interesting.
Okay.
Like,
what?
Yeah.
So I just want to say that the proof goes by showing, so there is a paradigm in the Euclidean world, which is corona decomposition, which says that every surface of finite perimeter can be decomposed into pieces which are close to Lipschitz graphs. Okay, with controlled overlap, and this is the Carlson packing condition. I'm not going to go into it. It's a way to partition every surface in R3 into pieces which are close to Lipschitz graphs, and that reduces many inequalities from a general complicated set to a set which is a graph of a Lipschitz function.
Yeah.
And what we do is we do the same thing in the intrinsic world. So we say every surface, this is true in any dimension, can be decomposed into pieces which look like this. And therefore, it's enough to prove all of these inequalities when the set A is not a general set. It's, let's say, what's behind this graph. Like it's what an intrinsic Lipschitz half spaces. Okay, so remember there were these vertical transition things going up. So you see, you're going from inside to outside, and you have to count those things, but using these monsters. So using these classical results in harmonic analysis, but making them intrinsically non-commutative, we reduce the question. This is the first step in any dimension. This is not dimension 3 or 5, to proving it this isoperimetric inequality to intrinsic Lipschitz half spaces. To these guys. Yeah. Where are they? Yeah. Okay.
Right.
We reduce to that, you can say you're a masochist because it looks awful. But using this information in R5, we could prove the inequality. In R3, something more happened. We had to take a general graph and prove another structure theorem. You can see in this picture in R3 that even though this is a 3-dimensional object, it looks like it has 1-dimensional features, like this foliation by 1-dimensional lines. Stare at it. And we had to formulate in what sense we can take one of these curtains and make it into a Venetian blind to understand what is the 1-dimensional foliation. And that's this is what's called a foliated corona decomposition. And we understood what these, so we first partitioned your boundary of the set into pieces which look like these intrinsic Lipschitz graphs. And in R3, we do a second partition which discovers the Venetian blind structure, these 1-dimensional foliations of it. And then that reduces the inequality to a 1-dimensional inequality, which is easy to prove. Yeah. But in the end, there is a structure theorem about how do surfaces look.
Yeah, I think we have to study your pictures and your to see the geometry and how it interacts.
I know clearly I went too fast.
I hope that you'll give us your pictures and let us put them on the website, link to your talk.
So absolutely, I'll give these pictures, but also the paper is online. It's on my webpage and it's on the archive. And the part, and there's going to be a recording of this talk in which I go very fast in the end. Obviously, there's it corresponds to an explanation in the introduction of what we do, and you can just read the overview over there, and you can get it with more details. And also available if you email me, but it's all online and it's all available. And this will be also available.
Great. So thank you very much, Assaf, for wonderful talk and introducing us to ideas that are different from what we ordinarily hear. Thank you. Thank you.
Thank you.
So I think the discussion has gone on for quite a long time, and we have other classes now. So I'm going to end the talk, but I think we should continue our discussion informally, and people should contact you. And
I'm available.
We really would like to understand how these fit into quantum versions of your inequalities. So thank you very much, and we'll see you again next week. Bye-bye.
Thank you very much.